All right, sorry to keep you guys waiting. We'll get started now. So today we're going to cover actor-critic algorithms, which are going to be the next class of reinforcement learning algorithms that we'll learn about, which we'll build on the policy gradient material from earlier this week. But first, a few class notes. So homework 2 is out at this point, so hopefully all of you have turned in your homework 1. If you're using a few late days for that, keep in mind that you have only 5 late days cumulatively over the whole semester, so make sure you get your homework 1 turned in. Homework 2 will be due at the end of the month, and make sure to start early on that. So for this one, it will be a bit harder. So homework 1 was really meant to kind of exercise your ability to just do a little bit of supervised learning and play around with some very simple algorithms. Here you'll actually be implementing policy gradient reinforcement learning, which might take a little bit more time and a little bit more debugging. And remember to start forming your final project groups. So the proposals are due on September 25th. Definitely make sure that you get your group together soon and get your proposal written. All right, today's lecture. Today, we're going to talk about a way that we can improve on policy gradient reinforcement learning by introducing something called a critic. So we'll learn about what a critic is, how we can train a critic, and how we can use it to get a better policy gradient. And a better policy gradient usually means a lower variance policy gradient. We'll talk about something called the policy evaluation problem, which is essentially the problem that we're solving when we fit a critic. We'll talk about discount factors, which are a convenient way that we can handle infinite horizon problems, which we'll talk about more in today's lecture. And then we'll introduce the complete actor-critic algorithm and a few practical instantiations of that method. So the goals for today will be to understand how policy evaluation fits into policy gradients, understand how actor-critic algorithms work, and also see a few practical examples of this. All right, so let's briefly recap what we saw on Monday with policy gradients. So on Monday, we basically went through the derivation for the reinforce algorithm, which I have summarized here on this slide. So the reinforce algorithm consists of 3 steps: generating samples from your current policy, so that's the orange box; calculating an estimate of the return, that's the green box, and then using that estimate of the return to calculate a policy gradient, which is then used to improve the policy by taking a step in the direction of the gradient. So you can kind of imagine the green box in the policy gradient algorithm as a very simple, very rudimentary way to evaluate how good your current policy is, simply by summing up the rewards along your trajectories. And we call these things Q hat. So we had a version of the policy gradient that we wrote out like this. We said that it's grad log pi times the total reward from time step t until the end, which we called Q hat. So Q hat is an estimate of the return that you will get if you take this action A in state S and then follow the policy, and that estimate is obtained by summing together the rewards that you actually saw after taking that action. So we call this the reward to go. Most of what we'll discuss today will deal with better ways to estimate the reward to go. So far in policy gradients, we saw that the reward to go was just estimated by using the actual rewards that you saw along that one trajectory that you executed. But of course, in reinforcement learning, we're dealing with stochastic environments and also stochastic policies. So if you were to teleport yourself back to this state, take that same action, and then run your policy again, you'll probably get a slightly different reward, because even from the same state and from the same action, at time step t plus 1, you might land in a different state. You might take a different action at time step t plus 1, and so on. So if you were to somehow teleport back to the state and do this many times, you would get different values for your total rewards. And what we want when we're estimating Q hat is we really want the average of all of those, which we're crudely approximating with just a single sample. So Q hat is essentially the estimate of the expected reward if you take action A in state S. So can we get a better estimate? So visually, you can think of it like this. Let's say that this is our trajectory that we executed. This is the state ST. And in that state ST, and for the action AT, we're trying to estimate Q hat. And the way that we estimate Q hat in the regular policy gradient algorithm that we saw on Monday is by summing together the rewards that we actually got along this trajectory. But if we were to actually repeat this multiple times, basically teleport back to state SIT and take the same action AIT and then execute our policy again, we would get a variety of different outcomes. And what we really want, if we want to get a better estimate of Q hat, is to somehow average together all of those possible outcomes. So what we really want is we want the sum from time step t until the end of the expected value of the reward, given that at time step t we took action AT. So if we somehow knew the true expected reward to go, rather than the single sample estimate that we use in the policy gradient, we could plug that true expected reward to go into the policy gradient, and this would be a lower variance policy gradient. Why is it lower variance? Well, it's because if you're using a single sample to estimate the expectation, you compute your estimator multiple times, you'll get slightly different answers because that single sample will change. But if you average together all possible trajectories, then of course you will get more consistent gradients if you do this multiple times, because the true expected value, of course, doesn't change. So if we somehow knew the true expected reward to go, our policy gradient would be a better policy gradient, a lower variance policy gradient, which means that we could take bigger steps, or we could learn faster, and so on. Now, what about the baseline? So, of course, in reality, we always use a baseline version of the policy gradient. So we wouldn't do grad log pi times q. We would do grad log pi times q minus some baseline. So before we saw how we could use the average reward as the baseline. So what are we averaging now if we somehow have this expected reward? Well, we would average together all the expected rewards for all the different actions. So what we can do is we could average together all q values for all states. But actually, it turns out that it is perfectly allowed to actually use a state-dependent baseline. So if you go back to I'll leave this as a homework exercise to you, but if you go back to the lecture on Monday, you can actually rederive that whole proof for how the baseline is unbiased for the case where the baseline depends on S, and you'll actually find that it still averages out to 0, which means that you can use a constant b, or you can use a b that actually depends on SIT. And if you want to use a b that depends on the state, then the equivalent of the average reward is the average q value from that state, which of course is the value function that we saw last week. So one very nice thing you could do is instead of just average together all q values, you could average together all the q values from that state S and plug that in there, and then you'll have an even lower variance policy gradient. This quantity q minus v, as we discussed last week, it quantifies how much better the action AT is than the average action from that state. Because the value is literally defined as the average q value averaged over all the actions distributed according to your policy. So q minus v quantifies how much better the action AIT is than the typical action the policy would take. That means that that value is positive for actions that are better than average and negative for actions that are worse than average. For that reason, we call this the advantage and denote it A. So the advantage of an action literally just means how much better is this action than the typical action. So if you see somebody write grad log pi times A, all they mean is q minus v, which is the advantage. Okay, so I covered value functions and q functions last week, but let me just briefly recap this. So the q function, this thing that I've been using to replace the reward to go, is defined as the expected value of the reward summed over all the time steps from the current one until the end, conditioned on being in a particular state at time step t and taking a particular action AT. And usually we'll write the q function with a superscript pi to denote that all these expectations are taken under a particular policy pi. The value function is exactly the same way, only it's conditioned only on a state rather than a state and an action. So the value function can also be defined in terms of the q function as the expected value of the q function, where the expectation is taken with respect to the action. Or you can also define it as a sum of expected rewards, conditional on only the state st and not on the action at. Those are equivalent. And then the advantage is basically the difference of the two. It tells you how much better is at than the average action you would take from your policy. So then we can write out our nice baselined lower variance policy gradient as the sum of grad log pi's times the advantage. The advantage for which policy? The advantage for the current policy. So the better that we can estimate this a pi, the lower the variance of your policy gradient will be. Of course, usually you don't know exactly what the advantage function is, so you have to use various approximation methods. So the policy gradient that we saw on Monday, this policy gradient, is an estimate of the advantage, because it's a difference between the rewards you got for taking some action minus some baseline, which doesn't depend on the action. So it is an estimate of the advantage. It's just not a very good estimate. So this quantity is unbiased, meaning that in expectation it will give you the right answer, but it's a high variance single sample estimate of the advantage, which means that if you were to basically teleport back to state SIT, take action AIT again, and then roll out the rest of the trajectory, you would get different estimates of the advantage each time you did that, which means you have high variance. But it is unbiased, so it's a correct estimate and expectation, but you can do better. So when we talk about doing better, what we really mean is doing a better job of that green box. So remember, for the policy gradient, the green box, the fitting the model or estimating the return, estimates this quantity. So essentially all of today's lecture will be about how do we do a better job of estimating that quantity. So the policy improvement will still be a gradient step just like before, but when we talk about fitting a model or estimating the return, now we're going to somehow estimate q pi, v pi, or a pi, and we'll aim to get a better estimate than what we could get by just summing up the rewards along a single trajectory. All right, so let's talk about how we can do this. Let's start with the following question. If we're going to talk about fitting value functions, the question is, what do we fit and what do we fit it to? So we could fit we could fit q pi, so we could actually build a neural net that directly estimates q pi. We could fit v pi, or we could try to fit a pi. Does anybody have any thoughts about, why might we choose to do one or the other? Like, should we go with q pi? Should we go with v pi? Should we go with a pi? Any guesses? Any opinions? Yeah.
Well, you can derive v pi from q pi and then a pi from the previous two, so you just need q.
All right. So the answer was, well, you can get v pi from q pi, and then you can get a pi. So all you really need is the q. That's reasonable. Like, you can recover everything else from the q. Any other answers? Did you have a different answer?
Well, I agreed with
Okay.
a pi because a pi, once you fit it once, as your pi changes, then you'd have to refit your model again and again and again. But with q pi, you already have a decent model that you can then just update a little bit.
Right. So the answer for those of you that didn't hear is, it seems like a pi is very, very strongly dependent on your policy, whereas q pi might, kind of change a little bit more slowly. So even if your policy changes a little bit, you can just update your q a little bit. That's actually true. So that kind of suggests that maybe q pi is a good thing to fit. Any reason why we might want to fit something other than q pi? What's like a downside with trying to fit q pi? Yep.
Dimension is bigger. Fits in states and
Yeah, it's bigger. It depends on states and actions, whereas the v depends only on states. Okay, so there are a few trade-offs, and in fact, different algorithms will actually fit different things. So I'm going to discuss the classic actor-critic algorithm in today's lecture. There are other answers as well. So there are, in fact, algorithms that fit q. So q is equal to the expected value of the reward. And a very convenient thing about this is that the expected value of the first reward is actually just a scalar number. It doesn't depend on any random variables because the state and the action are given. So you can equivalently write the q function as the value of the reward at time step t, because that doesn't depend on anything random, plus the expectation in the future. And the expectation in the future, of course, is the expected value of the value function at state t plus 1. Of course, you don't know what that state is, so you have to take the expected value with respect to that state. So the Q function is equal to this, the current reward plus the expected next value. And now, what we could do is we could say, well, if we have a good estimate of the value at time step t plus 1, maybe it's okay if we're a little bit crude about how we evaluate this expectation. And the way that we can be a little bit crude is we can just say, let's use a single sample estimate for just st plus 1, but still plug in the full value function at that time step. So this full value function will take care of all the paths branching out from st plus 1, but we'll just ignore the fact that there are many other st plus 1s we could get and use a single sample estimate. Still unbiased, because in expectation these will all average out, but it's not equal now. This is approximately equal, because you might have other st plus 1s if you try multiple times. But it's a pretty decent approximation for your Q function. And now, if we want to write out the advantage, which is what we're actually going to plug into our policy gradient, the advantage is just the current reward plus the next value, which is how we're approximating Q, minus the current value. So that suggests that maybe, if we don't want to fit a function approximator to something that takes in states and actions, it's actually almost enough to just fit the value if we're willing to pay a little bit of a price for using that single sample estimate for st plus 1. So we do pay a little bit of a price, but it's a small price because it's just one time step, not all the time steps. And it saves us having to fit a function approximator to both states and actions. So in fact, classic actor-critic algorithms will in fact fit the value function v pi, but there are also other actor-critic algorithms that we could derive that do fit Q. So today we'll talk about the ones that fit V. Later on, when we talk about Q-learning and off-policy algorithms, we'll actually also cover methods that fit Q. Okay, so for now let's just fit V, because that way we have fewer inputs to deal with. So we'll have our neural net. Our neural net will take in S. It will output an estimate of the value function. And let's say that the parameters of this neural net are called phi, because we already used theta to denote the parameters of the policy. So for the value function, we'll say that those parameters are called phi. All right, so we decided what we're going to fit. Now, what are we going to fit it to? So figuring out what to fit it to is the problem of policy evaluation. So policy evaluation basically says, given a fixed policy pi, figure out how good it is, which means figure out its value function. And of course, if you have the value function, you know how good your policy is, because the reinforcement learning objective, as we saw last week, is just the value at the initial state. Or if you have multiple initial states, then it's the expected value over the initial states. So how can we perform this policy evaluation? Does anybody have any ideas? How can we estimate how good our policy is? Yes?
We do the same thing that we've done in the past to estimate these things. We just generate a bunch of samples, and then we figure out what the value was for those samples, and then we fit it to that.
Right. So do exactly what we did on Monday. Just generate a bunch of samples, use those samples to estimate how good your policy is. There's your estimate. So let's do that. This is called Monte Carlo policy evaluation, and that is basically what policy gradient actually does. So policy gradient, when it sums together those rewards, is doing Monte Carlo. So let's do Monte Carlo. We'll say that the value at a particular state is roughly equal to the total reward that you actually saw when you visited that state from there until the end. Of course, it's not actually equal to that number, because if you were to revisit that state multiple times, you might get slightly different outcomes afterwards. But it is a single sample estimate of the return from that state. So you go to the state, you sum together the rewards you saw from there until the end, and if you had the luxury of being able to teleport back to that state, you could do this multiple times, but we don't, because this requires us to be able to kind of reset the world back to a previous state. So we just do a single sample estimate. Okay, so this is the estimate we're going to do. This is our neural net. Sum together this stuff. Now, here's a question for you. If we were to use these estimates, somehow it kind of seems like there's there's something a little funny going on, right? So we talked about how we want to use these value functions to avoid having the high variance that we get from just plugging in the sum over the rewards into the policy gradient. So now we said, okay, instead of plugging in the sum of rewards into the policy gradient, we'll plug in, let me back up a little bit, we'll plug in the advantage right here, estimated using values. You'd think that would be better because the value functions hopefully give us a better estimate of these expectations. But now we're saying we're going to estimate the value functions by using the same single sample return estimates. So is this all kind of fake? Like, do we have any reason to believe that this will help? Does anyone have any hypotheses about why this might help or why this should not help? Yes?
It should end up helping to some extent because we can imagine a world in which our system of VPIs gets overdefined, and so then our approximator will have to come up with something that is kind of close to all the different points it's trying to match, which we could then, in theory, believe would be a more better generalized pattern.
Yeah, so the answer for those of you that didn't hear is that, well, you might kind of hope that your function approximator, when it's sort of given a few conflicting targets, will sort of average them out, and as a result, generalize a bit better. Okay, that's one hypothesis. Any other hypotheses? Anybody want to take a stand against the single sample estimator? Okay. So yeah, my hypothesis was kind of like that too, which is why I drew this picture. So for those of you that didn't quite understand this argument, maybe I can clarify it a little bit with the picture. So if you were to just fit the value function with the single sample estimator in a single state, obviously you wouldn't be able to gain anything from that. But we're not fitting it in a single state. We're using the same neural net to fit these Monte Carlo targets in a variety of different states. So while you might never visit the same exact state a second time, perhaps in some of your other trials, you visited other states that are not exactly the same, but are kind of close. And maybe the return you got from here was quite different than the return you got from here, but these states are kind of similar. So now your function approximator will share some of the something between these two states. So if it got plus 1,000 here and plus 800 here, it might say, well, these are pretty similar, so I'll just average that out and say they're both roughly plus 900. This basically amounts to saying that your function approximator generalizes to some degree and doesn't overfit your data. That's a fairly reasonable thing to expect. So because of this effect, because you really are fitting one function approximator to all of these target values, you can actually get some sharing between the states, and as a result actually end up with better estimates of the expected return than you would if you were to just plug that sum directly into the policy gradient. So it's not as good as teleporting back to the same state and literally taking multiple trials from that same state. It's not as good as that, but it still gives you something. It's still pretty good. So concretely, the way that, yes, question?
So how does it know that that other state is close to it?
Yeah, the question is, how does it know that this state is close to this state? It doesn't. So this is where the magic of function approximation has to come in. Of course, in reality, what happens is that your function approximator will make its best effort fit. It'll sort of it'll fit the data as best it can. If you regularize it a little bit, maybe it'll try to not overfit, and then it will average together some things and not others, and it will make mistakes, and it will decide that some states that are actually very distinct from each other but just look similar are in fact similar. Some other states that look different but in fact are actually very similar underneath are in fact distinct, so it'll make mistakes. Yes?
So Q, B, and A, we're all trying to fit the word to go, right? So shouldn't the time step we see the state be a very important parameter for estimating that?
Sorry, shouldn't which time step?
The time step that we see the state. Because if I see
Ah.
A at 0 versus
Okay,
the last step.
it's a subtle comment, and let me explain this a little bit. So far, everything I've described is in this finite horizon setting, where we're summing up the rewards from the current time step t until the end, capital T, which means that the numerical values for the value function will change drastically as the time step changes. So the value function at the last time step just involves summing together one reward value. If you have 1,000 time steps total, then the value function at the first time step involves summing together 1,000 different values. So later on in today's lecture, we'll actually see how we can transform this into an infinite horizon problem where this issue doesn't exist. But for now, the issue most definitely does exist. And if you want to fit value functions accurately and you actually have a finite horizon problem, then typically you do want your value function to depend on the time step. There are a variety of ways to do this. You could essentially pretend that the time step is appended to the state. If you're using very simple classes of value functions, so not neural nets, but something like linear value functions, you might even just have a totally different value function for every time step. In general, we're going to avoid having to deal with finite horizon problems by essentially switching everything over to an infinite horizon discounted formulation, which we'll do in the second half of today's lecture. But if you actually have a finite horizon problem that you need to solve, then yes, you need to have things depend on the time step. Any other questions? Okay. All right, so many of you may have probably guessed this already, but the way that we're actually going to fit this value function is that we're going to construct a training set. So the training set will consist of inputs, which are all of the SITs that we saw, and outputs, which are the sums of the rewards from SIT until the end. So those will be the labels. We'll call those YIT. And then we're just going to solve a supervised regression problem. We'll fit the parameters phi so as to minimize the regression loss, which is the difference between the output of the neural net at that state and the target value y at that state. So this is just a regular mean squared error regression loss. Plug that into your favorite supervised learning package, get back a neural net. Okay, can we do better? So our ideal target, the targets that we would really like to have for our value function fitting, are these sums of expected values. And so far we saw that one of the ways we can estimate these expected values is by just taking the sample that you actually executed in the world and summing up the rewards along that sample. And we saw how that could be somewhat better than just directly plugging those sums into the policy gradient. Can we get a better target? So far we saw this Monte Carlo target. One of the ways that we can get a better target is by doing the same trick that we did before when we were talking about whether to use Q's or V's. We can write out this sum of expected values recursively as the first reward plus the expected values of all the subsequent rewards. Right, so this is exactly what we did before when we wrote out Q equals R plus V, except here I'm not even, what I'm going to do is I'm going to discuss what to put in here, right? So before we wrote R plus V, that required us to make a little simplification because the V, in fact, the target, the value at the next step has to be in expectation with respect to a distribution over the next state. But we can neglect that and just say we'll use a single sample estimate and plug in the V for the state that we actually saw at time step t plus 1. That's exactly what we can do here too. So if we actually knew V pi at the next time step, we could just plug that in there, and we could just say that the expected total reward is the current reward plus the value at the next time step. There is a problem, though, which is that V pi is exactly what we're trying to fit. So we don't know V pi yet. So what do? Well, we just do the next best thing. We just say, maybe the previous V pi is kind of close. If your policy changed only a little bit, that's actually not an unreasonable thing to do. It's incorrect. It's not the right V pi, but it's probably kind of close. So perhaps what you can do is you can just plug in your V hat pi subscript phi from your last training iteration. And while it'll not give you exactly the right values, it might give you a better estimate of the expected return than if you were to just sum together the rewards you actually saw. So these give you an unbiased estimate of the return, but a high variance one because it's using a single sample. This gives you a slightly incorrect estimate. So the euphemism we use for that is we say that it's biased, which is basically just a synonym for incorrect. But it has lower variance because this thing was calculated by averaging together a bunch of different samples. So it might be closer to this integral numerically than any single sample that you actually took. So in practice, this can actually work quite a bit better, especially if you have very stochastic policies or very stochastic environments. So directly use the previous fitted value function. So now if you do it that way, then you still have a supervised regression problem, and just your training data now, instead of using the sums of rewards as the labels, uses the reward you saw at that time step, plus the value at the next state that you saw, evaluated using your previous value function estimator. It's biased, which means somewhat incorrect, but in practice it might actually be a better estimate because it has much lower variance. Yes?
So would we just initialize our V estimate to like the single sample?
Right, so what the question is sort of getting at is, initially, on the very, very first iteration, your previous value function is a bunch of garbage. It's like initialized with random weights. So what do? Well, you have to initialize it in some way. Initializing with Monte Carlo returns is a pretty good option. We're going to, let's see, am I going to discuss this later in this lecture? So what I'm going to discuss later in this lecture is actually a way to do a little bit better than just doing R plus the next V. And we'll talk a little bit about things like eligibility traces and generalized advantage estimation, which make it a little less sensitive to that initialization. Yes?
For a finite horizon problem, that estimation has capital T time periods, right? But you're summing now to one more, so now it has T plus 1.
Yep.
So it keeps increasing.
I'm going to talk about that in 2 slides, I think, or maybe in 1 slide. Yes, that's coming up very shortly. OK. But to just conclude this discussion, we still call these Y just like before. We still solve a supervised regression problem like before. People typically call these a bootstrapped estimate. So if you see someone say, I'm using a bootstrapped value estimate, what they mean is they're doing R plus V. And if they say, I'm using a Monte Carlo estimate, that means that they're doing this sum. OK. A few examples of policy evaluation just to sort of give you a bit of intuition for what you actually get when you fit these value functions. TD Gammon. This is a reinforcement learning program for playing backgammon, created in 1992. It used an actor-critic algorithm. The reward was the outcome of the game, and the value function basically gives you the expected outcome given the board state. So the value function in this case actually has a very natural interpretation. So when you do policy evaluation, you're basically just saying, given this board state, how likely is my policy to win the game? AlphaGo, 2016, basically the same thing. The reward is the outcome of the game, which means that your value function basically tells you, given the state of the board right now and what I know about the capabilities of my policy, how likely am I to win the game? Very kind of natural, very intuitive quantity. All right, so we can at this point put these things together to build a complete actor-critic algorithm. So far I just talked about the policy evaluation step. How do we fit the value function? Now let's just put the pieces back together. Many of you probably already know what's going to happen here to get a complete reinforcement learning method. And at this point, this is going to be a complete actor-critic method, which is a type of policy gradient that uses value function approximation. So the structure of the method looks an awful lot like reinforce, except that we've added these additional steps. So we have a step 2 where you fit V pi phi to your sampled reward sums, and then you evaluate the advantage at all of your samples by taking the reward you saw at that step plus the next value minus the current value. And then you plug that into your policy gradient in step 4. So the blue box, the policy improvement box, is still a gradient step, but the green box now involves actually fitting this neural net V pi phi. And you can fit it to single sample estimates, which we called Y. You can also fit it to bootstrap returns, so the current reward plus the next value, which will have lower variance but somewhat higher bias, and both of those can be reasonable options. And now the next thing I want to talk about is that question that came up, which is that something is a little fishy with this kind of estimator, because if you make everything depend on time, like if you have a different value function for every time step, this is all fine. But if you have a time invariant value function, if you have a stationary value function for what is really a non-stationary problem, then your values will keep getting bigger, right? Every time you take an R plus a V, if the rewards are always on the order of like 1, then your targets will go up by 1 every single time you do this. That doesn't seem like the right thing to do. So we can actually fix this. So we can switch over to an infinite horizon formulation and make it so that these targets do not in fact diverge. And for that we need to introduce the concept of discount factors. So discount factors really deal with the problem of what happens when the episode length goes to infinity. But you can actually also use them with finite episodes. It's just they're easiest to motivate for infinite horizon problems. So you can have some episodic tasks, like, this is a robot learning to stack a Lego block in an episodic fashion. It resets every time, and the episode is of fixed length. But there are other tasks that are very naturally non-episodic tasks, tasks that are continuous or cyclical. So if this little simulator robot needs to run, and he just wants to run as long as possible, hopefully forever, this is really an infinite horizon problem. So in that case, of course, the way I've written out the bootstrap estimator, it can get infinitely large if your rewards are positive, or infinitely small if your rewards are negative. So what can we do? Well, there's a simple trick we can do, which is to introduce a little bit of an additional assumption to our problem, which is that getting rewards sooner is better than getting them later. So, if I told you right now that I'll give you $1 million, you might be pretty thrilled about that. But if I told you that I would give you that $1 million in a million years, you might be like a little bit disappointed. And if I told you that I'll give you the $1 million in a billion years, you probably just would think that I'm just joking with you. If I told you that I'll give that to you in 100 years, maybe you're a little more excited, because then, okay, maybe like your descendants can benefit from that. So somehow rewards sooner is better than rewards later for us, and maybe it should be better for our agents too. So what we can do to mathematically formalize that notion is we can say that our target values will now be given by the reward plus the next value multiplied by some constant, which I'm going to call gamma, and that constant will be some number between 0 and 1. 0.99 tends to work pretty well. So if you're not sure what to set it to 0.99. Okay, so that seems like a little bit of a hack just to get those sums to converge. Kind of a reasonable hack, perhaps. But what does this hack actually mean? Like, what does that assumption mean about the underlying MDP? Well, one way we can understand discount factors is we can construct an MDP that is equivalent to doing reinforcement learning in the discounted formulation, but without the discount. So if we have our original MDP, this is a little cartoon MDP with 4 states. You can transition between all 4 of those states. If we wanted to solve this MDP with a discount, that's the same as solving a different MDP without a discount. And that different MDP is constructed by introducing an additional event that can take place, which is very similar to the event that makes you prefer $1 million now over $1 million a million years from now, which is that you know that people are mortal, people die after a while, and therefore you might prefer getting those rewards right now rather than getting them later, because you're more likely to be alive right now than you are later. So we'll introduce the fear of death into our agent, and that will cause him to prefer getting the rewards sooner rather than later. So we introduce a state, which is the death state, and this is a very simple model of mortality. Your probability of dying is 1 minus gamma at every single time step, and if you die, then you do not collect any more rewards. So it's sort of I guess an atheist view of existence. No rewards after death, only before death. And that means that your expected value in this death state is 0. So you could imagine that what is really going on here is it's gamma times v plus 1 minus gamma times 0. So this additional modification to the dynamics actually models exactly what's going on here. And then your probability of transition to this is 1 minus gamma, which means that all of your other transitions are just now modified by multiplying them by gamma. And if you work out all the expected reward calculations in this MDP, you'll get back basically exactly this equation. All right, that seems kind of reasonable. We can think about what this looks like, for example, for policy gradients. The easiest way to do this is to just plug it into an actor-critic algorithm like this, but we can also plug in discounts gamma into policy gradient methods, including Monte Carlo policy gradients. So there are a couple of actually ways to do it, and the different options will actually shed some light on the role that discount factors can play. So one fairly obvious option for plugging in a discount factor into a Monte Carlo policy gradient is to take that reward to go quantity, and when we calculate the reward to go, just multiply each of the rewards in that sum by gamma to the power of t prime minus t. So that means that the first reward in the sum gets a multiplier of 1.0, the second one gets a multiplier of gamma, the third gets a multiplier of gamma squared, and so on and so on and so on. That seems like a reasonable thing to do. Another option would be to step back a little bit and look at our original policy gradient, the one before we used that causality trick to distribute the sum inside of the sum over log pi. Instead, go with the original reinforced formulation and plug in the gamma there. So now our policy gradient is the sum of the grad log pi's times the sum of the rewards, and each of the rewards in that second sum is multiplied by gamma to the t minus 1, which means that the first reward on the very first time step gets a multiplier of 1, the second gets a multiplier of gamma, the third gets a multiplier of gamma squared, and so on and so on. These are not the same. These are actually now two different gradients for two different reinforcement learning problems. So which one is the right one? There's a question for you guys. Which one, do you guys want to venture a guess as to which one is better, more correct? Yes?
Option 1, because we don't want to discount past rewards, which I think option 2 does.
Okay, so one answer is maybe it's option 1 because we don't want to discount past rewards. Yes?
I'd also argue it's option 1 primarily for the argument that like once we hit like t equal to like 2000 something, in option 2 our decision at t equal 2000 means absolutely nothing, because at that point our reward to go is effectively 0 no matter what we do, but in option 1 it still actually means something.
Right. So another way to rephrase this is that in option 2, because of how these discounts end up playing out, you essentially kind of don't care as much about your decisions in the future, which seems a little peculiar. Okay, well let's unpack these a little bit and try to see what the relative merits of these are. First, one thing we can think about is, well, what does the actor-critic solution do? So if you just plug in your gamma into your bootstrap estimate, this is what you end up with from actor-critic. Which one of these two does this correspond to? Okay, who thinks that this is a lower variance estimate of option 1? Who thinks it's a lower variance estimate of option 2? Okay, you guys are not sure. So this one basically is going to correspond to option 1, because here you are not, you're just, if you imagine what this value is going to be, inside of that value it's an estimate of the reward at time step t plus 1, that's multiplied by gamma, plus the next one, which comes from the bootstrap, which is going to be multiplied by another gamma, so it's going to be r plus gamma times next star plus gamma squared times next star, and so on. So this one, the option, the actor-critic option, will correspond to option 1. And these are not the same. But let's talk about option 2 a little bit. So for option 2, you can actually do the same, causality and distributed thing, but now you will actually get a different number in here. So once you actually apply causality and this distributed stuff, then here you have an exponent of t prime minus t. Here you have an exponent of t prime minus 1. So you basically have different discounts for your grad log pi's at different time steps. And what that means is specifically that for later time steps, the grad log pi is just multiplied by smaller numbers. It's multiplied by rewards that are more heavily discounted. So another way that we can see this is we can make this exponent be the same as in option 1 and take the remaining gamma to the t minus 1 term out of that sum and put it in front of the grad log pi, and that maybe makes it a little more obvious how option 2 compares to option 1, because in option 2 everything is exactly the same, except that now the whole thing is multiplied by gamma to the t minus 1 for that time step t. So your gradients are essentially discounted the later in time they occur. Now, in some sense, this is actually not entirely unreasonable, because if the reason we introduced this discount is because we're afraid of death, well, it kind of makes sense that I wouldn't worry so much about what I'm going to have to do 100 years from now, because I think, well, I'm less likely to be alive 100 years from now, so I'd rather optimize for having the right behavior right now than the right behavior in the future. If I have limited representational capacity in my policy, I'd rather have a policy that does the right thing today than a policy that does the right thing 100 years from now when it's less likely to matter. So in some sense, in the original motivation we had in terms of reformulating the MDP using discounts, this is actually the right answer, in that this is actually correctly solving that MDP with the probability of death. But it kind of seems a little uncomfortable. Like, it kind of seems like this is maybe closer to what we really want. So this discomfort is real, right? So the death probability is option 2. Option 2 is not what people typically use. What we typically use is option 1, and that's what you get if you use discounts in actor critic. So why is that? What's the kind of mathematical interpretation of option 1? Which problem is it actually solving? That's actually a fairly deep question, and it's a little bit involved to actually derive the answer to this. It is not solving the MDP with the death state. It's doing something else. So one interpretation of this is that what option 1 is really doing is it's actually optimizing for a truly infinite horizon problem, one where there is no probability of death, like the running guy here, but it's doing so in a way that avoids having these infinite sums. So let's think about what happens as you increase gamma. As gamma goes from 0.99 to 0.999, 9999999, etc., etc. What happens is that these sums become bigger. And as gamma approaches 1, the sums approach infinity. But if the multiplier on the grad log pi gets bigger, that means that the variance also gets bigger. So if the value, unless the quantity is actually deterministic, which it isn't, as it gets bigger, its variance gets bigger. And that gives us an alternative interpretation of gamma. Gamma can also be seen as a way to limit variance. So what you want is you want to maximize expected reward for an infinite horizon problem without any discount, but then you have infinite returns, which means you have infinite variance, which means that you cannot actually produce any reasonable estimate of your policy gradient. So what you do instead is you put in a little hack that reduces your variance to a finite value, and in fact, the lower that gamma is, the lower your variance will be. Of course, if your gamma goes to 0, your variance is 0 because everything is 0. So gamma allows you to trade off between bias. Bias is what you get as you reduce gamma, and variance, which goes down the lower gamma is. So if you want to learn about how option 1 can be shown to be an approximation to infinite horizon average reward reinforcement learning, check out this paper by Philip Thomas called Bias in Natural Actor Critic Algorithms. I'm not going to go into that in more detail, but the high-level intuition is that you can view gamma as this way to limit variance in a problem setting where you would actually have infinite variance if you were to not use gamma. Okay, so now we can summarize the actor critic algorithm with the discount. That's where the discount is. You can actually also derive an online version of the actor critic algorithm. So the observation you can make here is that with policy gradients, we needed to sample multiple trajectories, and they had to be complete trajectories so that we can sum up the rewards along those trajectories. So with policy gradient, you can't just stop in the middle of a trajectory rollout, update your policy, and then keep going, because you need the whole trajectory to get those total rewards. But with actor critic, you can actually evaluate an estimate of your advantage every single time step. You don't need to see the rest of the trajectory, you just need to see the very next state. So you can actually derive an online actor critic algorithm like this. You take an action A sampled from your policy to get a state, an action, a next state, and a reward. Then you use this to update your value function estimate using the target R plus gamma times the next V. Then you evaluate your advantage. Then you evaluate a single sample estimate of your gradient, but plugging in that advantage. And then you take a gradient step. And that's a fully online algorithm, meaning that you can make these updates every single time step without even generating full trajectories. So that's kind of neat. I'm going to tell you right now that just implementing this naively, it usually won't work. So you'll have to wait until after the break to find out how to make it work. So at this point, we're going to take a 2-minute break, and I'll see you back here at 11:04, and then we'll talk about how to make online Actor Critic really work. Hello.
I have a question about D and how it supposedly doesn't take an action as an input.
Okay.
Do you mean that you don't need to generate new actions to evaluate it? Or
No, no. All I meant was that. So the Q function is a function of a state and an action. The value function is a function of a state. So that means that if you were to train a neural net to approximate this, that neural net needs to take an S and A as an input, whereas the value one only needs to take an S.
Right, but then the value function is dependent on like the reward, which is dependent on A, right?
Right, so it depends on a policy, which is why we put a policy at the top. But in terms of the actual difficulty of the learning problem, like if you imagine doing, let's say, least squares instead of a neural net, right? So the number of values that you have to fit for least squares increases as the dimensionality of the input increases. So if the dimensionality of A is like similar to S, this might have half the number of parameters. That's all that means.
So then, yeah, how does it evaluate the reward function, which depends on A?
Well, so everything is in expectation under pi. So the definition of the true value function is the expectation under pi of the Q function. So it's basically calculating which reward you would get on average, averaged over pi. So the actions come from pi.
And it's like an estimate.
Yeah. All right, please find a seat, and we're going to resume. All right, let's talk about a few kind of implementation details for actor critic algorithms. So this is the actor critic algorithm, the online version of the actor critic algorithm that I had before. There are a couple of choices that we can make when we actually go to implement actor critic algorithms. One choice we have to make is what kind of network architecture to choose. So a very simple, very straightforward choice is to have two totally separate neural nets, one that takes in S and outputs the estimate of the value, and a second one that takes in S and outputs the probabilities over the actions. This is a nice choice because it's simple, it's easy to implement. It does have some downsides, which is that if your states, for example, are extremely high dimensional, extremely complicated, you might want to share representations between your value function and your policy. So if you, for example, these are images and you have a convolutional network, probably the first and second layer convolutional layers are going to need to be pretty similar for the value function and policy, so it might make sense to share them. So you could do that too. You could have a shared network design where you have some layers that are shared by the value function and the policy, and then you have two separate heads for them, which is to say two separate stacks of fully connected layers branching off from them. Generally, the trade-off is that the two-network design is easier to implement. It's simpler and it's more stable, meaning that you don't have to tune your hyperparameters as hard to make it work. But you don't have these shared features between the actor and the critic. If you share weights, then the trouble is that you have two very different gradients, one from the supervised regression from the value function and the other one from the policy gradient, hitting the same shared layers. And figuring out how to balance those gradients so that one doesn't kind of obliterate the other can be a little tricky, and it might require a little bit of care in terms of how you tune learning rates and things like that, especially since the variance of policy gradients tends to be much larger than the variance of your supervised regression objective. Making online actor critic work in practice. So there's a big problem with the online actor critic algorithm that I actually wrote out here, which is that it's requiring you to take a gradient step with a mini batch size of 1. That's a bad idea even in supervised learning. So in practice, if you really want an online actor critic algorithm like this to work, and you don't want to do any kind of fancy off-policy thing, which we'll discuss in a subsequent lecture, you probably need to use parallel workers. So the way that you would do this is you would have multiple workers in parallel so that you can have a batch of size greater than 1 for step 2 for the value function fitting, and a batch of size greater than 1 for step 4, which is the policy gradient estimate. The simplest way to do it is to have a synchronized parallel actor-critic algorithm where you have multiple workers, essentially multiple simulators running in parallel collecting these transitions, and then a synchronization point where you update, where you basically perform step 2, 3, 4, and 5 using a batch collected from those workers while the workers are paused waiting for you to finish your work until they can continue simulating. So mechanically what this might look like is if you're using like the Mujoko simulator, you might have 10 instances of the Mujoko simulator, have all 10 of them take a step, perform step 2, 3, 4, and 5 on that batch of 10, then have them take another step, and so on. And that will give you a synchronized parallel actor-critic algorithm, which can actually work, yes?
Actors running all the same policies?
Yes, so in this design, the actors would need to all run the same policies, but each of the workers would make different samples from the distribution, so they would have different random seeds, essentially. So that means that the actual actions that you take could be quite different, and the actual next states you get could be different, but the policies, the underlying distributions are the same. Any other questions? Okay. Now, you could also implement an asynchronous actor-critic algorithm, and I think if I have a couple minutes at the end of the lecture, I'll actually show an example of one. In an asynchronous actor-critic algorithm, it's very similar to asynchronous SGD. You would have a parameter server that keeps track of the parameters of your policy and your value function. Your workers would be running, at whatever rate they're running at, and they would, once they take the step, they would perform this update, exchange parameters with the parameter server, and so on. We'll discuss this design a little bit more much later in the course when we talk about parallelism and asynchrony in reinforcement learning. But for now, kind of the short version here is that if you want something simple that is mathematically equivalent to a correct actor-critic implementation, this is the way to go. In practice, people often use the asynchronous design because it tends to be faster and easier to implement because you don't have to deal with synchronization. Yes?
For the synchronous case, are they sharing weights for the value function?
Yes. So in the synchronous case, the only thing that's parallelized is the simulators. So all the value functions, all the policies are shared by everybody, and at the synchronization point, they're updated for everybody. So the parallel stuff, the blue lines, those are just the simulators, and all the simulators are executing the same policy, and the update is using one value function. Did you have a follow-up?
But isn't it usually the local time bottleneck is for the fitting rather than simulation?
Right. So the purpose of this parallelism here is not to make it faster. It's actually to make it work at all. Because if you don't have parallel workers, you have to make these updates using a single sample batch. And a single sample batch for any large neural net is never going to work. So even if you're doing supervised learning, you always use batches of more than one sample. If you want it to actually go faster, this will make it go somewhat faster if your simulator is expensive because you're parallelizing the simulator, but you're not parallelizing learning. If you want to parallelize the learning, you can also use multiple workers for gradient updates, and that would be kind of completely separate from this. So if you wanted a truly parallel asynchronous RL method, you would probably have multiple workers collecting experience and separately multiple workers doing gradient updates. And that'll be discussed in the parallelism and asynchrony lecture later. There was another question back there?
How do you deal with the fact that your policies are stale in the async approach?
Yeah, so the question is essentially that, as soon as this guy updates something, this other one is now executing the wrong policy. So isn't that incorrect? How do you deal with it? The answer is it's incorrect, and we sort of, cover our eyes and pretend that we don't see it and hope for the best. It's a very common exercise in deep learning, unfortunately. All right. On that note, let's talk about yes?
Just one last question. In the asynchronous setting, you still have to synchronize to get the reward or all these the actual data from each of the workers to update B and
Yeah, so to dig into the details of that a little bit more, like one way you could do it is you could just say that this worker doesn't actually update the policy. It's just they deposit their sample into the into their buffer, and you say, okay, once I have like 10 samples, then I'll update. and then those samples are stale to different degrees. But the goal of all this is to just avoid ever having to update with a batch that is too small. Because if you update with a really tiny batch, then you'll have really high variance and you won't make any progress. Okay, so let's talk about a different way that we can use critics. So far, I've talked about this way of using critics, where you basically use them directly to estimate the advantage. And on Monday, I talked about this way of estimating the advantage just using Monte Carlo estimates. And I've plugged in the discount here just to make them correspond to each other, so that they're actually estimates of the same quantity. So the nice thing about the extra critic way of doing it is that you have lower variance, because the critic hopefully gives you something that correlates with that integral that you want, the expected value. The downside is that it's not unbiased. It's not unbiased for two reasons. One reason is that you might have used your previous critic in fitting the new critic, and the other reason is that your critic is probably not perfect. So even if you had used Monte Carlo values to fit your critic probably made some mistakes. So these values aren't really correct values, and therefore your policy gradient is a biased policy gradient. The Monte Carlo one has no bias, but it has substantially higher variance because it's a single sample estimate of the whole total reward. So is there something else we can do? Can we, for example, use a critic to get an estimator that is unbiased but still has lower variance than this thing? Well, one thing we could do is we could use our critic not directly to evaluate the advantage like this, but just as a better baseline. We can use it as a replacement for B. So remember that the baseline can depend on the state, and it's still, and its expectation still works out to 0, and you can work that out at home. So I can substitute in for B any function of the state I want. And if I substitute in my estimated value function, that's actually a really good thing to substitute in there, because the value function is trained to be as close as possible to the expected value of these sums, which means that the value function will reduce, on average, the magnitude of this term as much as possible, which means that it will give me lower variance. So using a state-dependent baseline gives me better variance, and a very good state-dependent baseline is the fitted value function. And this is still unbiased, because I can subtract any function of the state, and in expectation, my gradient doesn't change. So this has no bias, and has lower variance. I'm going to skip this part, because actually, yeah, I think I have enough time to go through it. So this is more of a cautionary tale. So you might say that, let me just go through this. OK. All right. So you might say that if I estimate my advantages like this by subtracting the value, that makes things better. Therefore, maybe I can subtract something that's even more correlated with my total reward, which is my Q function. Right? So if I subtract value function, the value function is close to these total rewards. It's still, I told you that it's still unbiased. Great. So what if I just subtract Q values? Like Q values will perfectly cancel out these total rewards in deterministic environments. It'll just go to 0 if your critic is correct, assuming the stochasticity in the environment is negligible. So why don't I just do this? This part is actually not correct. So subtracting the value function, fine, because it depends on the state. Subtracting something that depends on the action, that is no longer correct. However, you can actually fix that up. You can actually add an additional term to compensate for the error introduced by the fact that your baseline here depends on action. At this point, we usually don't call it a baseline. We call it a control variate, although we sometimes call it an action-dependent baseline. And essentially, the term that you have to add back in is the expected value of this thing. So for a baseline or for a state-dependent baseline, the expected value is 0, so we don't have to compensate for it. For something that depends on the action, like the Q value, its expected value is no longer 0, so you have to add it back in. Now, you might think, that's a silly thing to do. If we knew what this number was, why do we even bother with all this policy gradient stuff? But what you can do is you can choose an approximation for your estimated Q values that makes this expectation tractable to calculate. And there are a variety of things that can make it tractable to calculate. For example, if your Q function is quadratic in the action and your policy is multivariate normal, the expected value of a quadratic function under a normal distribution can be calculated analytically. So this sample-wise estimate with the Q hats, that of course cannot be calculated analytically, that requires samples. But if you baseline it with a quadratic Q function whose expected value can be calculated analytically, you might actually get even lower variance. So in general, with control variates, the game that you play is you choose some representation for your control variate, for your Q here, whose expected value can be calculated more easily than using samples from the real environment. And there's a whole host of tricks you can use to do this. I'm not going to go into them in detail, but if you want to learn more about this, I would recommend checking out the paper called QProp by Shishan Gu from 2016 as a starting point to learn about control variates in policy gradient methods. And there are many, many different tricks that people have tried to basically plug in some kind of action-dependent term here, get the magnitude of this term to be really small, use this to take care of the bulk of the gradient calculation, and then just keep this thing around to essentially make the whole thing unbiased. And that's a very common kind of area of research right now for improving the variance of policy gradients. Okay, any questions here? All right. Eligibility traces and n-step returns. So far, I talked about the critic-based estimator and the Monte Carlo estimator, which can also use the critic as a baseline. So the critic-based estimator has lower variance, higher bias if the value is wrong. Using a baseline, even if it's a state-dependent baseline, has no bias, but potentially higher variance. So one tempting thing that we can consider is, well, if this has some advantages, this has some advantages, why don't we kind of interpolate the two somehow? Like, can we kind of combine the two estimators and get a single estimator that's as good as, you know, the best of the two? We can actually combine them, and we can introduce some parameters that will control the bias-variance trade-off more continuously than just this binary choice. So the intuition here is the following, that as you go further into the future, your variance increases, right? So especially for the single sample estimator. So if I generate one sample for, like, I don't know, what I imagine my career will look like over the next 30 years. I say, well, maybe I'll become an astronaut or something. Like 30 years in the future, who knows? Like any single sample estimate guess is not really representative of the total outcome. But for tomorrow, it's probably pretty representative. I'll say, oh, what am I going to do tomorrow? I'm going to go to work tomorrow. Like I generate 100 samples of what will happen tomorrow. In like 99 of them, I go to work. In one of them, like, I don't know, I get sick and stay home. So probably pretty representative of what's going to happen. But if I try to generate 100 samples of what will happen 30 years from now, there's so much variability between those that it's essentially useless. Like any one of those samples doesn't really tell me anything that would be helpful about what will happen 30 years from now. So you have much bigger variance further in the future here, and you have much smaller variance over here. And what that means is that these single sample estimators, like the Monte Carlo estimator, are pretty useful for getting accurate values in the near term, but next to completely useless for getting accurate values in the long term. And the value function based ones, these ones, they're kind of the other way around. Like they're going to be, their bias might hurt you a lot for things that are very close by because they'll be, you know, just as biased. But for things further in the future, their ability to integrate all of these different possible outcomes will result in much better estimates. So somehow I'd like to use the value functions for further in the future and the Monte Carlo estimates, the sums of rewards, for closer to my present time. So what I can do is I can essentially select where to cut. So I can say, let's sum together the rewards until the variances start getting too big, at which point we basically cut off our traces, meaning stop summing things together, and that will reduce all this future variance. So what I could do is I could introduce an n-step return estimator where I sum together rewards from the current time step until n time steps from now, and then just discard the rest. So that's represented by this green line here. So I just cut it off and this tail end here is just discarded, just thrown in the garbage. That might actually make sense because if I have very stochastic futures, that one trace where I become an astronaut 30 years from now is like so unrepresentative of the average outcome that I might as well just pretend it didn't happen and just pay attention to the near-term rewards. But I can actually do better if I have a value function, because what I can do is I can add back in my value function at time step t plus n to basically fill in this little missing piece. And so long as my value function actually somewhat correlates with the true values, it'll probably be better than not putting it in, because not putting it in basically amounts to saying, well, my value is just 0. And as long as it's a better estimator than the number 0, it'll probably help. So choosing n greater than 1 often works better, right? So this thing, the actual actor-critic return estimator, is essentially a special case of this where n is equal to 1. But why would 1 be the best choice? It's kind of arbitrary, right? So oftentimes actually values larger than 1 can work better. Any questions? Yes?
Is this basically like n-step look-ahead policy?
It's a little bit different. I mean, usually when people say n-step look-ahead, they mean that there's some kind of search going on. There's nothing intelligent going on here. It's not like you're thinking about which possible behaviors for those n steps will lead to better outcomes. This is really just a way to balance bias and variance. So all this is really doing is saying, I'll get bias from using my value function, so I'd like to not use my value function if I don't have to, but I'll get variance from using larger values of n, so I don't want to use values of n that are too large. Yes?
Do we get any improvement if instead of like a hard cutoff at a certain n step, we sort of like average between the two and
Yes.
more heavily?
Yeah, we get that improvement on the next slide.
Gotcha.
So on that note, let's talk about this. Do we have to just choose one n, or could we somehow do something softer? Like it's sort of, I intentionally drew it as a vertical cut. It looks very harsh, very abrasive. Maybe we can do a little bit better if we can not commit to just a single value of n, but actually average together multiple n-step estimators. And that might actually make it a little easier to turn this from a very peculiar integer value trade-off parameter, something that looks more like a continuous number that we can tune to get the best bias variance trade-off. So what we can do is we can essentially cut everywhere at once and then average them together. So we can say, here's our n-step estimator. Let's construct an estimator that basically consists of a weighted average of all possible n-step estimators. And I'm going to call this AGAE for generalized advantage estimation. So this might be better because you might say, well, I don't really know which particular one is good, but I know that like later, larger values of n are a bit better, but if they're too large, then they're not good. So I want to maybe pick a particular weighting scheme and average together all possible n-step estimators. There are a variety of weighting schemes you can choose, but a very simple one that leads to a particularly simple formula is if you use an exponential decay for the weights. So how do you weight? You can choose whatever you want here, but maybe you mostly prefer cutting earlier because you want less variance. That's why actor-critic just cuts right on the first step. So maybe we'll choose our weights to scale exponentially. So the first weight is going to be 1, the second weight is going to be lambda, the third one is lambda squared, then lambda cubed, then lambda to the fourth, and so on and so on and so on. So we'll have exponentially decaying weights. If you do that, then it turns out that you can do a little bit of algebra and simplify this weighted sum to a very, very simple formula. So I'm going to give you a little bit of a hint about how to start on that derivation. You can complete the derivation at home if you'd like. But essentially, the way that you can write out this weighted sum is you can say that your GAE estimator for this kind of exponential fall-off is the reward right now plus gamma times the next value. And the next value is now going to sum together two terms. It's going to sum together 1 minus lambda times the value function. So 1 minus lambda is the weight on cutting the trace at that point. So if you cut the trace, you get the v of st plus 1. So that's 1 minus lambda. And then lambda times what would happen if you didn't cut the trace. So basically, at every time step in the future, you get this linear interpolation. 1 minus lambda times the value for cutting plus lambda times the value for not cutting. So 1 minus lambda times the value function plus lambda times the reward plus the next thing. And the next thing just repeats. Gamma times 1 minus lambda v plus lambda r, et cetera, et cetera, et cetera. So you have this big set of nested sums, and each of those terms in the sum is a little linear interpolation. You can actually show with a bit of algebra that this thing reduces to a very simple formula. You can write it out like this. You can write it as a sum from the current time step until infinity of gamma times lambda to the power t prime minus t times this thing called delta. And delta, surprisingly enough, is actually exactly the thing that we feed in as our advantage estimate in actor critic. So delta is just reward plus gamma times next value minus current value. So if you evaluate your value function at all your time steps, calculate these deltas, and then calculate a weighted sum of those deltas, you will actually get the average over all possible n-step returns weighted by an exponential fall-off, where the number in the exponential fall-off is given by lambda. And you can check the math for this with a little bit of algebra at home. This is a little bit illuminating to me because the fact that gamma and lambda are just multiplied together like this before being exponentiated suggests something about the role of gamma in advantage estimation. It suggests that in much the same way as lambda acts as a trade-off parameter between bias and variance, so does gamma, right? Because they're just being multiplied together. So that means that the role of lambda is similar to the effect of a discount, and vice versa. The effect of a discount is similar to the role of lambda. That is to say that they're both serving to interpolate between high variance and high bias estimators. So this further kind of reinforces the point about discounts being a form of variance reduction. Okay, so to review and conclude, we talked about actor-critic algorithms, where the actor is the policy, the critic is the value function. That gives us a policy gradient with reduced variance. We talked about policy evaluation, which is basically fitting a value function for a given policy. We talked about discount factors, which can be interpreted in different ways. They can be interpreted as fear of death, or they can be interpreted as a kind of variance reduction trick. And the latter one is maybe a little bit more true to how we use it in practice. We talked about the design of actor-critic algorithms, how we can have one network with two heads or two networks, how we can do kind of this batch mode or online version, and how we need to do parallelism if we're doing online. We talked about state-dependent baselines, which are another way to use the critic, and we talked about combining critics with n-step returns into this GAE-style estimator. There are a number of examples of actor-critic methods. This video that I kept showing with the little humanoid robot falling down, that is actually an actor-critic method using the GAE-style estimator with policy gradients. Here's an example video for an actor-critic method that is actually using the online formulation with multiple parallel workers. So this is from a paper called Asynchronous Methods for Deep Reinforcement Learning, which introduced an algorithm called A3C. So it's an online actor-critic method parallelized to get multiple batches. So if you want to learn more about that, check out this paper. Some suggested readings. So this is my last slide. If you want to read more about actor-critic methods, this is a classic paper that you may want to check out that actually sets up actor-critic algorithms with value function approximation and connects them to policy gradients. And these are a couple more recent papers. Here's the QProp paper that talks about action-dependent baselines. All right, so I'll see you all next week for a discussion of value functions and Q functions.